ladies and gentlemen, in the right corner, weighing 160 pounds, it's Patrick. Hi. Welcome to Genesis London Conference 2018. This means that in 2019 there will be another one. So thank you all for being here for the first Genesis London Conference. And what an amazing venue is this. Can I get a round of applause for the beautiful, the view on the other side of the building. I mean, it's an amazing, amazing venue. I'm very happy to be here. As you can tell from my non-accent, is that I'm not based out of London. I was born in Rotterdam, raised in Rotterdam, and now I live in Amsterdam, which is just an hour away of this beautiful city. But for me, as an Amsterdammer, I have never seen Amsterdam from 32 floors up, because there's no building that high. So it is an amazing view, and I'm very happy to be here, and I'm very thankful that you are all here. Can I get a round of applause for the venue and today Binary District event here from you? Perfect. I'll tell you a little bit about myself after I give you some household info, because it's always important to get things going right. So first of all, if you are not on the Wi-Fi, there's a Wi-Fi signal here. It's open. There's no password needed, and nobody's sniffing the data, so it's very secure. The hashtag for today. So if you want to do anything on Twitter, or there's no Telegram group, unfortunately. But if you want to do something on Twitter, I'll be watching the Twitter stream. The hashtag that I'll be watching is Binary District. So please use that in your tweets. You probably know that this conference is organized by Binary District. And there are some partners, supporters basically, that make this possible. So I like to thank them briefly. Blockchain Institute, Zcash, IBM Waves platform, Ergo platform, and Primal Base. Without them, it wouldn't be possible to have a venue like this, speakers like this from all over the world. And I think the tuition was like 40 pounds. So that is an amazing effort from those partners. So a little bit about me and maybe why I'm here. I'm the co-founder of TeamW, the Next Web, which is fairly well known, I think, nowadays, a digital media company. We're based out of Amsterdam, but we're more known in the US, and actually a lot of our traffic is coming from London, so thank you very much for that. It's the second city for us. A little bit of background why I am very enthusiastic about blockchain and cryptocurrencies is when I was 14, I read the Financial Times, and I learned all the stock prices every day by head. So you could go you could come to me and say on any day, and you could say like, hey, what's Philips trading at? And I would say like 25.70. And I always had like a few percent. I was a few percent off, but I was always interested in that. And then when I was 18, I decided to go and work at the stock exchange in Amsterdam, and I was the youngest trader at that point in Amsterdam, and I traded over 10 billion guilders, which is about 5 billion pounds, in 10 months. But I was also known as the Dutch Nick Leeson. I don't know if you know Nick Leeson, but Nick Leeson, there's a beautiful movie about him. He made some mistakes, some trading mistakes, and that costed a couple billion. I made the biggest mistake in the Dutch history And that I blame it because there was no blockchain yet. So this was 1998, and the trading floor was basically open outcry. So you can still hear it in my voice a little bit. I'm a little bit hoarse. So there was open outcry, mainly meaning that if you looked at the movies and you see all these people 60-bit, and all of a sudden they're screaming, and that's how you get trades done. So I was on a very, very busy day. I got like 5 minutes before the floor was closed, I got an order to buy 20,000 July 60 call options. So on ING. And when you work at the stock exchange, you hear everything. So your ears are trained in a different way. So I could hear people that are like 40, 50 meters away. I could hear them speak. And I was really good at, like, it's very, very nice to have skill if you're in restaurants. I can follow like 7 different tables. But my girlfriend doesn't really like that. But I can then say, well, they were talking about this, they were talking about that. But so I heard that the July 60 call was trading at 420, and there were 2 people that were selling at 420, and I was like, 420, that's a great price. So I run into the pit. I said, July 60 call, 20-bit, and 2 people said, sold. And this is kind of like, the pit is like this big as the stage here, but then with 100 people. That's a little bit how it works. So I was standing here, and the other 2 are over there. I said, I'll buy 20,000. 20,000 options is times 100 is a lot of shares. So it was a big trade, and so how it worked, you write down, like, I bought 20,000 options at 420 from these 2 people. And then they write the same thing. I sold 20,000 options at 420. And then it's like paper. You write it down, you tear it off, and then you put it together somewhere in a bin. And then, so that's very old-fashioned, right? So, but I didn't look at what they said. So right now we had a trade. I thought I bought 20,000, but the prices were rising as crazy. It was like Bitcoin today, right? You don't know what the price of the next in the next minute will be. So the prices were rising. So what they bailed out on me, and they just bought the minimum amount that they needed to buy, but they didn't say it to me. So I thought I bought 20,000. I went back to the client. I said I did you the deal of the century, because it's already trading at 520. I bought them at 420, but I actually bought just 20 options, not 20,000. So later on, I needed to buy 19,980 options when the price was a lot higher. And I told my manager, kind of like, I don't think we should buy now. That's what Nick Leeson did as well. I don't think we should buy now. The price will go down. He was like, well, you might be right, but that's a liability. So then I needed to buy it back, and an hour later we would have made a lot of money on this. But now it was I think we lost over 100,000 euros, which was more than my salary. Anyway, so I was always into trading, and that's why I'm also very excited about this moment, because blockchain is changing the way we set up companies. It's changing the way we deal with a lot of complicated stuff in the world, and I believe that the technology is going to make a big difference in our lives. And that's why it's very exciting for everybody to be here and to learn more. There's one story that I want to share. When I first encountered Bitcoin, when I first heard about it, I was walking in San Francisco, and I was with my, it was 2011 or 2010, I don't recall exactly, but I was walking there, and with my phone in my hand, and somebody, I was standing, waiting for a traffic light. Somebody next to me said, like, "Hey, I see you're reading the Next Web." I was like, yeah. He's like, "Oh, cool." I was like, yeah, thank you. Do you know it? Yeah, I know it. And I was like, "Oh, why do you know it?" "Well, I work here." And so we started chatting a little bit, and so he invited me to his office. And he was working, or his company was an exchange that traded Bitcoin. And I was like, "What?" I don't know. And this was 2010. He said, "Oh, let me show you. So this is how you create an account, super simple." And so now the Bitcoin is trading at 76 cents. So I put an order in for 10,000 Bitcoin at 76 cents. And then 2 minutes later, I was like, "Well, the trade is done. So now I have 10,000 Bitcoin." I was like, "Good for you, man." And so then we started talking about golf, and he invited me to play golf the day after. And I was like, and then he said, I really advise you to go in and buy some of these Bitcoins today on my platform. It's like, yeah, I'm going to do that. So I went home, and then I opened up my laptop. I was like, okay, I'm going to do this right now. And then an email came in, and I was like distracted. So I went to work on these emails, and later on I had to buy these Bitcoins when they were over 2,000, trading at over $2,000. So that was a little bit of on the one hand serendipity, because I bumped into this great guy. We're still friends, or at least I call him a friend, but I don't know if he he made so much money that I don't I don't know if that's still applicable. If you still have friends, if you have so much money, so I'm very happy that I don't have that much money. But I'll ask later on. I think a lot of you are into some Bitcoin, either Bitcoin or other altcoins. So I'll ask you later on about that. But there is. I had a moment about a month ago, and I have two kids. One is my daughter is 1 year old, and my son is 2 years old. And when I was young, I got a bank account, and my grandparents put like 100 euros on it, and that was it. And then when I was 18 with interest, it was like 150 euros or something. So I was like, okay, so, but what if my kids are 18? Are we still using money, or what is, I can't predict that, but I was like, well, maybe I should buy them some cryptocurrencies. So, and then there's tax laws in the Netherlands that you can't necessarily buy crypto, or you can't buy anything for your kids and give it to them. So I thought, let's do it a bit different. So I drafted up a contract where they both are borrowing money from their dad, 5,000 euros, which is a lot of money if you're one. And they borrowed that money, and they invested it in crypto. So it's untaxed, and with this, my daughter, Denne, is 1 year old, and my son, Bo, are the two youngest crypto traders in the world, which is, I'm very proud. I'm very proud dad anyway. So you can talk to me about kids anytime. You can wake me up. But it's also a passion of mine. I'm very much looking forward to today. I'm pretty sure I'll learn a shit ton, because I've spent some time with some of the speakers yesterday already, and sometimes I kind of like tuned out a little bit. I was like, well, I pretend that I understand what they're talking about. So don't worry if you don't understand everything. There is enough room for during the coffee breaks to figure out, like, what was he talking about? What was she talking about? And I hope we'll learn a lot and have a great day. And I'm very confident that we will have a great day. And with that, I'd like to ask Margarita to come onto stage. Come on, please. And give her a round of applause. Margarita is the editor-in-chief of Binary District. She's also up for a PhD on journalism. And yeah, you're very excited about the blockchain, and you're going to enlighten us a little bit and open the day.
Thank you so much, Patrick. Is it on? Yes. Yeah. Okay. Basically, what I wanted to talk about is about myths on new technologies. Blockchain as one of the new technologies that are coming to our lives. The first question is, where do myths come from? In our everyday life, we rely on our knowledge and experience and critical thinking when we try to understand something, including the technology. And now we are pretty good with learning the gadgets and apps, how to use them, and so forth. Pretty short period of time. But in case of new technologies like VR, artificial intelligence, blockchain, Internet of Things, big data, machine learning, we have to rely on opinion leaders, which are quite often represented in media. So why new technologies? Why so many myths about them? Being in the technology area for around 10 years, I also tried to get some experience at least of VR or IoT. So how does it actually work? How do I actually use them? So I actually went to different companies that tried to implement VR, for example. It was a gaming company, and so I put the glasses on, and then there was a game, and I thought, okay, so that looks pretty weird. So the experience itself is pretty weird at the moment with new technologies, including VR. And after 10 minutes, just 10 minutes of using VR, I felt so sick, so that and the sickness continued for almost 2 days. And okay, is it a good experience? Maybe not that good. Then I was thinking, okay, so artificial intelligence and machine learning. So if we're talking about robots, okay, so here we have now Sophia the robot who can come up with some interesting jokes and so forth. But if you actually talk to linguists and those who develop machine learning from those who research this area, they say like whatever she says is just pre-programmed. And the same was some fun experience during some conferences I went to where there were some interactions with robots. They can't do much, even though we get those scary envisions of our future, I don't know, in Black Mirror or in Westworld. But what the biggest achievement that the robots made by far is that they learned how to open a door, or how to carry one bag from one spot to another spot. So, or IoT. I was pretty impressed when talking with the developers of IoT in the industry of shipping and logistics. So there's some pretty exciting things going on. But if we talk about smart homes, a fridge talking to a toaster, they're actually needed. They want to have that kind of experience. And also, when you go to different conferences, you maybe notice, like, if you don't have IoT or blockchain or, I don't know, big data or VR attached somewhere to your stand, so probably there is not enough interest, so no one will come up to you. Or you won't get enough investment. Also, if you go to conferences and listen to all the talks, the majority of them are very marketing-oriented, right? And if you read the articles, the majority of stories you get is like 10 ways blockchain is going to disrupt this and that, or 5 ways VR is going to change your life. Or they tell you some spooky stories about how robots are going to take over, they're going to take over your jobs and so forth. So the loud ones so far in the area of new technologies are those who are trying to sell you something, trying to get some investments. And another funny thing, at least from blockchain area, is like it's just enough to write one book, have one TED Talk, and then become the biggest experts in blockchain, and then sell your talks for $15,000. My vision is, what we need to do is we need to bring more researchers, more developers into the area of new technologies. Otherwise, we're going to end up like this with the academic road. So researchers and the academic community, they just seem to be missing out the whole public debate and only used occasionally by certain media or conferences, events, just to prove certain points or sell something. So is it because they're much less presented, in different event platforms or even on the internet? For example, Google doesn't rank academic journals too high. And social media also have their own logic, like they filter through posts, through opinions, through articles shared, and researchers are not there either. So the involvement of developers and researchers might actually have helped to bring all these nuances of new technologies back in the storyline. But unfortunately, they're mostly ignored by the media. The books of researchers rarely become bestsellers, and their audience mostly consists of academics themselves and the students at the universities. So does it mean that the researchers should just retreat from the public debate and keep the truth to themselves? Certainly not. And they should continue to actually engage and present their research to wider audience wherever it is possible. They should initiate and participate in public debate, even on Twitter, for example. And not everyone will hear them, but in the end, their expertise might sometimes just make a difference. And that's how the idea of binary district journal came around. With binary district, what we try to do, we try to spotlight those behind the innovations. We try to kind of change the narrative in the mainstream media and maybe produce more analytical articles, talk directly to those who develop the technologies, and of course debunk certain myths that were already created by media. And that's why we also have binary districts as such, the one that arranged this conference for you. Mostly because we want to provide this platform and bring together those who are in the know and those who want to know. And we really like to see, as many of you at our events, we have events in Amsterdam, in Berlin, in London, and also Moscow. So just follow us on Facebook, Twitter, at Binary District. And if you, for example, would like to contribute to Binary District Journal as a writer or as a columnist, or if you would like to give some interviews or comments to us, just drop me a line at editor@binarydistrict.com, and you'll be the ones presented among our thought leaders. So basically that's it. Thank you so much. I pass the word back to Patrick.
Thank you. The Binary District Journal is very interesting to read. I can recommend you all to go there and read some of their articles. We often try to repost some of their articles on TeamW because they're just really good. So I'm very happy with Binary District and that it's here. Next up is the COO of Zcash. Who in the room here owns Zcash? Oh, wow. Okay, that's quite a lot, actually. So Jack is based out of London. And so, as I said, he's the COO of Zcash. And I don't know what it's trading at the moment, but after this talk, it probably goes up. So if you have time, just go along right now. Jack, there you go.
It might not go up, you might listen to what I have to say and decide that it's not such a great idea after all. But I'm not going to be talking specifically about Zcash. I'm going to be talking about privacy and confidentiality techniques in general, not just for cryptocurrencies, but for blockchain technology. Let's see if this, do we have, yep. So why do we need, also, by the way, I know that we're running slightly behind, so I'm going to zip through this quite quickly. And then if there are specific areas that people want me to dig into, they can raise it during the Q&A at the end. Or I'll be around for the rest of the day. And also we have one of our scientists here today. He's going to be speaking later on, Professor Ali Ben-Sasson. And if you really want to find out about the science behind it, he's the man to speak to. Okay, why do we need privacy and confidentiality with blockchains? Well, who here would like for all the details of every single financial transaction they undertake, from receiving their salary to paying their rent or their mortgage, to which magazines they subscribe to where they shop, to be published on the internet for everyone to see? Hands up, anyone? No hands? One person at the back is keen for that to happen. Well, in that case, then you're probably not going to be too worried about this, but it seems like the majority of people are keen to keep their financial affairs relatively private. And the reason that this is a problem for blockchain technology is that the way that what I call first-generation blockchain technology, as exemplified by Bitcoin, works is you have an input to a transaction and you have an output, and in order for that transaction to be proven to be valid, you have to prove that the inputs equal the outputs, so you're not making money out of thin air. You have to prove that you have the right to spend the input coins, and that's you prove that by using digital signatures. And you have to prove that the coins haven't previously been spent, and that is achieved by looking back through the ledger, the entire history of the blockchain, and checking to make sure that those specific coins haven't already been spent. Now, the downside of all of this is that there is no privacy. People used to say that Bitcoin was anonymous. I think now everybody recognizes that it is in fact pseudonymous. If you can associate a specific Bitcoin payment address with a real-world identity, then you can see what payments are flowing to and from that. You can start to link payments together, and you can end up doing what's generally referred to as transaction graph analysis, where you can figure out where the funds are flowing, and if you can identify, say, a specific exchange deposit address or a specific vendor, and you see somebody's paying money into that, receiving money from it, then you can draw certain inferences about their financial transactions and relationships. There are a number of ways, a number of approaches to getting privacy and confidentiality. One of the very early approaches that Satoshi Nakamoto himself advocated was the use of one-time payment addresses. This is not ideal because implicitly you have to generate a new one-time address for every single person that you transact with. And if you want to consolidate your funds into a single address or account, then there's inevitably going to be linkability there. And that is what enables transaction graph analysis. Also, with Bitcoin, although they're starting to decline now, there were various mixing services where you could put your coins in, have them mixed around with a whole bunch of other people's coins, then have them spat out to a new address, and that would break the linkability between addresses. There were services on Bitcoin, and there are certain protocols now that are emerging, both for Bitcoin and on other cryptocurrency or blockchain platforms. These are, again, are less than ideal. There's something implicitly concerning about having your coins, which can be traced back, having coins that can be traced back to their source, mixed with a whole bunch of other people's, and there may be issues there where you need to be able to demonstrate the provenance of assets for legal or regulatory reasons, which hopefully is something that will as Bitcoin and as cryptocurrencies become more widespread in usage, we hope that we'll start seeing a lot more acceptance of them, and that will inevitably include regulatory acceptance and legal frameworks around them. You can restrict access to the blockchain, which obviously restricts the utility of the blockchain itself. It's also no good if the individual participants of the blockchain want to conceal their activity from the other participants in the blockchain. And of course, if the blockchain itself is leaked, then all of the information becomes available to the public. You can encrypt the transaction details, but that means that you can't then necessarily spend the assets that you've received. It may protect some details of a transaction, like the information that's passed along with a transaction, but it affects the ability to spend the assets. It means that the assets can't be fully fungible. You can store sensitive information off the chain. So you could simply write a hash of a transaction, say, to the blockchain, and have all the details, the source, destination, and amount stored off the chain. That implicitly gives up many of the advantages of a blockchain. It means that it's no longer a single source of truth. And again, you give up advantages like having fully fungible assets on the blockchain. Finally, there's a lot of work emerging in the area of side channels and payment channels. They are primarily, at the moment, the focus is on enabling scaling, particularly, for example, with the Lightning Network for Bitcoin. But they also can bring advantages in terms of privacy, because the transactions can happen off the chain, not necessarily exposed to the entire world. But at the end of the day, when you open and close these channels, you inevitably disclose the balances between the parties that are a party to those channels. So those are the low-tech ways of adding privacy. What I'm now going to focus on a little bit more time on is the use of cryptographic techniques to add privacy and confidentiality. The first one that is quite widely used is what's called stealth addresses. So this is a solution to the problem of one-time addresses, where you have to generate a new address for everyone that you want to interact with. This is a technique that allows the sender to generate the one-time address, and then you are able to scan the blockchain and see which payments are intended for you. And there's not necessarily any way to link those addresses together. A passive observer doesn't have the ability to link those addresses together. You still have the problem that if you consolidate these payments into a single address, then it's possible to link them, but it certainly removes a key obstacle, a key usability problem with one-time addresses. And that provides privacy for the recipient. So here we're starting to break things down into which element of the transaction is protected or made confidential. You've got the sender, you've got the recipient, and you've got the amount that's been transacted. The next technique is known as confidential transactions, and that uses a cryptographic technique known as Pedersen commitments with range proofs. What this does is it exploits a technology called homomorphic encryption, where you can perform addition or subtraction on encrypted values and achieve effectively the same result as if the values were not encrypted. So here we have two inputs that, when added together, equal the sum of the two outputs. And with additively homomorphic encryption, which is what Pedersen commitments enables, you can encrypt the inputs, and the sum of those encrypted values will be the same as the sum of the encrypted output values. So what it means is that you can prove that the inputs to a transaction are equal to the outputs, but without having to disclose what those inputs and outputs are. The use of range proofs means that you avoid a scenario where somebody creates a negative input in order to try and create money out of thin air. Range proofs are used to prove that the values are greater than 0. This has been implemented in the Monero cryptocurrency last year very effectively. All of these techniques end up having implications for performance or usability. In the case of stealth addresses, there's a very small increased computational cost in scanning the blockchain for transactions. In the case of confidential transactions, you end up with larger transactions simply because of the size of the proofs. There's also a technique that's been developed by Chain to conceal the type of asset being transferred if the blockchain is capable of supporting more than one asset. Next up, we have ring signatures. Many of you will be aware that this is used in the Monero cryptocurrency, and this is quite a mature piece of cryptography that allows the sender of a transaction to conceal his identity amongst a ring of other potential senders. So you can what the ring signature allows you to do is it allows you to prove that the transaction was created by one of the keys in the ring, but it's not possible to determine which key was used. So you're effectively hiding yourself amongst a group of other people. It is a finite group. Those other people don't necessarily, they don't have to agree to participate in that group. It's a purely passive technology. And double spending is avoided by using a tag, which makes it obvious if the same person tries to use the same key to spend twice. This provides privacy for the sender, not for the recipient and not for the amount that's being transacted. And again, it increases the transaction size by a smaller amount than confidential transactions, and it's been implemented in the Monero cryptocurrency to good effect. Here's an example of what it looks like. Here we have a bunch of transactions where we can see on this screen what the input transaction is, and then these are the other transactions that have been included in the ring. So you can see here for transaction 1, this is unspent transaction output number 1, and it's going to number 7. Input 1, output number 7. This is the God's eye view of or the view of what's actually happening. To a passive observer, it looks like this. They know that there's a transaction that had an output of UTXO number 7, and they know that there were 3 potential inputs, but they don't know which input is the real one. Now, this is cryptographically secure until such time as somebody does something foolish, like creating a transaction that has got a single input and no other keys in the ring. At which point, you can go through a process of elimination. You can say, well, for transaction 4, it can't have been number 7, so we can write that off, which means that because transaction 4's output was transaction 10, that means that 6 must have been the input for that transaction. And by a process of elimination, you can start to weed out and figure out what some of these, what the source of some of these transactions were. You can go to monerolink.com for an illustration of how this was used on an earlier version of Monero. They have since introduced improvements like enforcing a minimum ring size, and also they've added confidential transactions, which make it a lot more difficult to track the transactions through, if not impossible at this point. And then we come to ZK Snarks, which is what Zcash is based on. ZK Snarks are a type of zero-knowledge proof, and I'm sure Ellie will correct me here if I get this definition wrong, but a zero-knowledge proof is a protocol which makes it possible to prove a statement without revealing anything other than the contents of the statement itself. Getting thumbs up, good. Snarks are a specific type of zero-knowledge proof. Many zero-knowledge proofs were originally interactive, where there had to be rounds of interaction between the prover and the person verifying the proof. Snarks were a key advance in that they are non-interactive, and also they are succinct, i.e. shorter than proofs used to be, which makes them usable in a situation like a blockchain. You generate a Snark proof to prove the validity of a transaction, and what it does is it provides the privacy for the sender and also conceals the amount that's being transferred. It's implemented in Zcash. So in Zcash, you can send transactions transparently, which are almost identical to Bitcoin-style transactions, or you can shield your funds, and you can transact them using shielded transactions. And this technique is used to protect shielded transactions. This is roughly how it works. You have an input, and attached to that input is the proof of validity for the transaction. The output is effectively the information that the recipient will need to create the next input, encrypted with their private key, and we use a technique derived from stealth addresses to ensure that it's not possible to identify the recipient. So the combination of those techniques means that the identity of the sender, the amount being transacted, and the identity of the recipient are all kept confidential and private. The Snark proof itself proves that the assets being used as the input exist and they've not been previously spent. It demonstrates that the creator of the transaction has the authority to spend those input assets, and it also proves that the inputs equal the outputs. As with all of these techniques, there are trade-offs. With Snarks, we have larger transactions than simple Bitcoin transactions. We also need to generate a set of shared parameters that gets used in generating these snark proofs. There's a proving key that is used by the person who's sending the transaction, and then there's a verification key that is used by the miners and the recipients to verify that that proof is correct. In generating these parameters, there's a side product or a byproduct created, which we refer to as the toxic waste. And if somebody were able to get hold of that toxic waste, they would be able to create false proofs, which would effectively allow them to counterfeit Zcash. Now, in the original launch ceremony back in 2016, we distributed the generation of those of these parameters across 6 different people, and each one of them then destroyed their computers afterwards to make sure that it would be practically impossible for somebody to get hold of all those different shards of that toxic waste and reassemble it. So we have a high level of confidence that nobody has access to that toxic waste. We're currently going through a new ceremony which has been improved. We're expanding the number of people that can participate. I think it's up to something like 25 people now have participated in that ceremony, and we'll be implementing that later this year. There are scalability limitations with this technique. There is a finite number of transactions that can be added to a blockchain that use this specific approach. Currently on the Zcash blockchain, that's 250 million transactions. And we expect that to increase later on this year. And the biggest obstacle, I think, currently is that generating these proofs is computationally intensive. Right now, it takes about 37 seconds on our benchmark CPU to generate a snark proof. The performance is very much dependent on the speed of the CPU, so it varies an awful lot, whether you're using a laptop or enterprise-grade hardware. The improvements that we've been working on over the past year that we're currently getting ready to launch later this year will drop that down to 7 seconds, possibly even lower. And we're hoping that that will make it possible for broader use of shielded transactions, and most importantly, increase the number or percentage of shielded transactions as compared with transparent transactions on the Zcash network. So those are techniques that are in use today, that have been deployed, that are currently being battle tested. I'm now going to cover briefly a number of techniques that are emerging, are in development, or have not yet been fully deployed in a production environment. The first one is Mimblewimble. It's been around for a couple of years. I believe there is a testnet up and running, and that uses some of the principles behind the CoinJoin mixing protocol and confidential transactions to combine all the transactions in a single block into a single transaction. One of the, I think it's likely that it would have been considered for adoption by Bitcoin were it not for the fact that it's incompatible with Bitcoin scripts. There's then another technique called scriptless scripts, which uses Schnorr signatures to prove correct execution of a script, or you could describe it as a smart contract. And what this effectively does is you have a smart contract which is not exposed on the blockchain itself, and you create a signature which is effectively a proof that that smart contract was executed correctly. This is compatible with Mimblewimble, so we may in the future see these two technologies being combined. And another technology in this space is bulletproofs, which have emerged quite recently. And these are effectively a kind of a replacement for the Pedersen commitments and range proofs in confidential transactions, and they use a different type of zero knowledge, of non-interactive zero knowledge proof to prove that the inputs equal the outputs for a specific transaction, which again allows the amount that's being transferred to be concealed. And the reason that they are attractive and interesting is because they're more than three times as efficient as Pedersen commitments, and they're a lot more efficient than ZK Snarks are currently. Later on today, Professor Ben Sasson will be talking about scalable transparent arguments of knowledge, and I'm sure that you'll see a Game of Thrones derived logo on the screen for that. And we're very excited about that. These are zero knowledge proofs that don't require a set of shared parameters in the same way that Snarks do, and which also have got the potential to solve some of the scaling problems that blockchains face. Some companies have been investigating the use of secure enclaves, such as Intel's SGX, to perform evaluation or computation on encrypted data. So what happens here is the encrypted data is published to the blockchain. The enclave holds the private key that's used to decrypt that data, perform the validation or the computation on it to prove that the transaction is valid or that the smart contract has been executed and to verify the output of that smart contract. But the actual data itself isn't available to the public or even to the owner of that hardware. And this is something that R3, the blockchain consortium, have been exploring for use in their Corda enterprise solution. Recently, Ethereum added some functionality which makes it possible to verify ZK Snark proofs in smart contracts. They did that at quite a low level by adding crypto primitive precompiled contracts. Now that's not going to make it possible to protect the actual Ether transactions, but it does make it theoretically possible to shield transactions of tokens within contracts. At the moment, the gas cost of verifying those Snark proofs is quite high. I think it's something like $20, but I could be wrong on that. But I would expect that technology will improve and that cost will come down, and we'll start seeing that becoming more widely used in the coming years. There's a lot of interest in the use of Ethereum for enterprise use cases, and various techniques have been developed. There's a company here in London called Clearmatics who have implemented ring signatures with stealth addresses they're working with the utility settlement coin, which is a group of banks including UBS, Santander, and others who are looking at the use of blockchains for the settlement of securities trades or making international cross-currency payments. Their approach uses what we call active mixing, which avoids some of the problems that I pointed out earlier with regards to the passive approach to ring signatures. JP Morgan have got their own fork of Ethereum, which is intended for financial sector use cases, and they have developed an approach which they call Constellation. And what this does is it shifts the smart contracts off the public chain, so that the details of the smart contract are exchanged directly between the parties to that smart contract, and then it means that the logic is kept off the chain and away from the public or away from the other participants in that blockchain. The problem is that because those private contracts can't affect the public state on the blockchain, it becomes difficult to prevent double spending. Fortunately, we have a solution for that in the Zcash technology, so we partnered up with JP Morgan to implement ZSL, which stands for something like the zero-knowledge settlement layer or the zero-knowledge security layer. And what this does is it implements the Zcash approach to shielded transactions within an Ethereum smart contract, allowing the shielded transfer of what we call Z tokens. And that works hand in hand with Constellation. It allows the business logic to happen within Constellation, and then for the settlement of any obligations, any payments, or the transfer of securities that arise out of that business logic to be carried out on the main blockchain, but protected by ZSL. And that was a very, very quick. How long did I run over? 1 minute. There we go. Are we taking questions now, or?
No, because
no. Okay.
we're a bit late. Yeah, I'm sorry. I have to be strict.
In that case, come and grab me during the day. I'll be around, and I'm on a panel later on
around
today.
Here?
Yeah.
Amazing. I was very impressed. So I hope I can.
Impressed by the speed of the content.
Both, and I hope I can talk to you later because my vocabulary went up by at least 20 words. So I'm gonna look that up later on. But thank you so much.
Brilliant.
Also, all the talks here. Give them a round of applause. Yeah. All the talks are filmed, and you can watch them also later. If you're like, what was that? What he said about the word that I didn't understand, and then you can, you can go back in time. Next up is Ido. Do I pronounce that in the correct way? No. Come up, please. And he is tied to the Cornell University in New York. And you have about 20 minutes to deliver your talk, and I hope it's just as exciting as the last one. Thank you. Give a round of applause.
Okay, thank you. So this is a project about a real-time cryptocurrency exchange. And with these guys, most of them are in Cornell University in the US. So the volume of cryptocurrency that is being exchanged right now is about $20 billion per day, an average fee of about 0.25%. It means that these exchanges are generating about $50 million in revenues per day. Those are ballpark numbers. So the problem with these centralized exchanges where all this trading occurs is that basically the way that it works, the users send their bitcoins or other cryptocurrency to the wallet of the exchange server, the centralized exchange, and then they can do real-time trading on the exchange. But there is some human on the other side, the server of the exchange, that can just steal all the money. So usually what would happen, the exchange will say, I got hacked. And in some of those instances, maybe it really was hacked. In other instances, it wasn't hacked. It was maybe an inside job. Cannot really be sure. But in either case, the user's money gets stolen. So I put in these bullet points some of the famous hacks of centralized exchanges. The most famous one in 2014, Mt. Gox. So 600,000 bitcoins were stolen. So the cryptocurrencies themselves, the bitcoins and others, are secure under standard crypto and majority consensus assumption. And there is a clean, simple question: can we have an exchange service between cryptocurrencies that is as secure as the underlying cryptocurrencies? Okay, so the answer to this question is yes, but it would be very slow. So this is like a slow interactive protocol between, let's say, Alice and Bob, who wants to trade Bitcoin for Litecoin. This is well known from about 2013, I think. So that would work. Alice would pick some random secret, and she would create, let's say, a Bitcoin transaction that spends her Bitcoins into an address that needs this random secret to be revealed. And if it is revealed, then the money can go to Bob, to an address that is controlled by Bob. Then Bob will use the same random secret and move his Litecoins, in this case, into an address that can be redeemed by Alice. If this random secret is revealed, then Alice revealed the random secret, and then Bob can and takes Bob's money, and then now Bob knows the random secret. He can take Alice's money. There is actually a security proof of this that involves some probability analysis. We did it because it is instructive towards the more complex protocol that we are going to use that rely on this kind of an idea. And it works okay, like this is secure as the underlying cryptocurrency themselves, but this is very slow. So you need to do the Bitcoin transaction. That takes 1 hour. And then you need to do the Litecoin transaction. You need to do these steps one at a time. So this is a slow protocol. It cannot really be used for a real-time exchange like the pit in the stock market where everybody is exchanging the currencies or whatever assets in real time. So there is this screenshot here. So this was implemented as a matching service in 2015, but this is defunct. Nobody was using it. So just because it is too slow. And there is a new hype about using atomic swaps. So this is about off-chain payment channels, where you can also do this cross-chain swaps between, if you have, let's say, a Bitcoin that is in an off-chain channel, somebody else has a Litecoin that is in an off-chain channel, you can do this kind of a swap between them. And this can work nicely for individual trades, but not as a real-time trading service with price discovery. So if you try to do that, you get to this kind of, so one way, simple way to do it is this kind of a hub and spoke kind of a topology with a server in the middle, but this has problems, so we can elaborate on that later. So another hype that has been, that's in the recent months becomes kind of a trend is decentralized exchanges. So again, the point of that, the main pitch of decentralized exchanges is that the exchange cannot run away with your money because the money, the cryptocurrency, is you deposit it into either the blockchain, the ledger itself, or to a smart contract on the ledger. And so this is controlled by the consensus protocol of the cryptocurrency. So that part is good, but can you really do real-time trades by doing transactions on a blockchain? So not exactly. Some of these schemes allow real-time trades, but there is some server that is facilitating these real-time trades, and now all the trade data is flowing into a central place. And now there can be several kinds of attacks, in particular front-running attacks that I will discuss in one of the later slides. And the other big issue, can you do really do what we call cross-chain trading? So if I have Bitcoin, somebody has Litecoin, somebody else has Ether, and we just want to do all of this trading, but if it were just tokens on a single blockchain, this is all of these, some of these decentralized exchanges are about just trading tokens on a single blockchain. If you want to do the cross-chain exchange, it becomes more difficult. So there is one approach using IOUs. We might not sound so promising, and another, this also doesn't really sound promising, is to have some committee that control the funds in escrow. Okay. So the project that we are implementing is using trusted hardware to facilitate a real-time cryptocurrency exchange. So at the high level, the idea of trusted hardware is that the hardware manufacturer, in our case, it's Intel SGX for the trusted hardware. So the hardware manufacturer, Intel, is going to embed some secret key into the CPU. And now you can have some known code that is known to the public that is running inside a secure enclave in the CPU. So this code is running with some input inside the enclave, and nobody outside of the CPU can see all the secrets that are being generated in the secure enclave. And the code is going to produce some output, and the CPU is going to sign that to produce a signature that says this is the computation that really happened, and this is done with this secret key that was embedded into the CPU during the manufacturing process of the CPU. And now it can be publicly verified by the corresponding public key that this was really the computation that the secure enclave did inside the CPU. So this is the idea. And I put some table chart here. That if you compare this to traditional, like pure cryptography, zero-knowledge proofs, this prover-verifier paradigm. So there will be other talks today, and the talk before my talk, that you get various parameters for the zero-knowledge proof that you can get with the trusted hardware. It's just an ordinary signature, so it's even more efficient. And the last column is also important, like when we talk about the zero-knowledge proof that we do. So let's say we do 64 invocation of SHA-256. It's like the computation before you convert it into zero knowledge is a very short computation. Like the enclave can run a computation for hours, days, weeks, years, and you can still create this proof that this is really the computation that happened if you are willing to trust the hardware manufacturer. Okay, so there are other use cases for trusted hardware and cryptocurrencies. In particular, there are nice features that you can get for off-chain payment channels. Also, there is a mixer for anonymity with thousands of inputs and outputs that you can do. So basically, if you are willing to trust the hardware manufacturer, you can get nice efficiency and features. But the point that I'm trying to convey in this slide is that with the real-time exchange construction that we are doing, it's actually less trust compared to what actually exists right now with all the centralized exchanges, where the users just move their money to the wallet of the centralized exchange, and the exchange can run away with the money. So in this case, the money is going to be controlled by this secure enclave that doesn't have a human element. It's except for this, whether the manufacturing process of the hardware was tampered with in a way that they shouldn't have been. But we can actually show that this is strictly more secure than just a centralized exchange, significantly so. Okay, so this is an illustration of how this trusted hardware-based exchange would look like. So say Alice is going to transfer. So the first step would be that the exchange server with this secure enclave is going to generate a new key pair of secret key and public key. And the public key is where, let's say, the user Alice is going to deposit the money to. So this generation of new keys is done using a fresh randomness that is known only to the enclave. And now Alice can send her money to this public key. And also there is a script that says if nothing happens and far enough in the future, Alice can get the money back. Bob will do the same. And they will give a proof that there are confirmations on the blockchain that this really happened. You give this proof to the enclave parses the proof, and then credits Alice, credits Bob in their accounts inside the enclave, and then they can start to trade in real time. So this is the basic idea. Okay. So now, one thing that we get from this that is really nice is this security against front-running attack. So this is an illustration of a sandwich front-running attack. So basically what's going on, there is, let's say, Alice and Bob. So Alice wants, let's say, to buy Bitcoin because she thinks that the price of Bitcoin is going to go up. Bob wants to sell Bitcoin for a lower price because he thinks that the price of Bitcoin is going to go down. So if I'm an attacker and I see all the trading requests that users want to do, so I can see that Alice and Bob send this buy and sell request, so I can buy the Bitcoins that Bob is selling and then sell the Bitcoins that I got for him to Alice and get a sure profit. So that's the kind of front running that you can do if you know all the communication that buy and sell requests that users want to do in real time. So the point is, in this previous slide, with this kind of an exchange service, there is no way. So the point is that what we are going to do, we are going to establish a secure communication channel between the users and the enclave. So the enclave is talking to the user's computer directly, and the data cannot be known to any human in the middle. So the buy and sell requests are known only inside the enclave, and now you cannot do this kind of front-running attacks because the enclave is running correct code. The correct code that is run inside the enclave, that all the users who want to participate and in the real-time exchange of this enclave, they know that this code is not doing any kind of front-running. So this is something nice that we get, unlike those decentralized exchanges and then, of course, the centralized exchanges. What is, let me say that when people talk about this trusted hardware, it's like a magical trusted party. You just assume that it exists, and then everything works. So in this case, for the front-running attack, it's kind of really true. Like there will be no front-running because this magical trusted party will not do anything bad. So the question is the entire thing completely trivial, or there are still interesting things here? So there are two answers. One is yes, one is no. So if you just want to do a real-time exchange of tokens on a single cryptocurrency, then yeah, this magical trusted party really gives you everything that you want in quite straightforward way. However, if you want to do this cross-chain trading, now you run into a real problem that is quite tricky to solve. This is what we call this all-or-nothing fairness problem, or you can also consider this to be an atomic commit that you need to do to several independent cryptocurrency systems. So this is the illustration. So let's say, so in my example, I'm assuming just exemplary numbers that Bitcoin is worth $4,000 and also a Bitcoin is worth 300 Litecoins. So Alice and Bob wants to trade, let's say, 1,000 Bitcoins for 300,000 Litecoins. So it's about 4 million worth of cryptocurrency that is being traded. So if they are doing this trading in using our exchange service, so Alice will deposit the 1,000 Bitcoin to the enclave, and then Bob will deposit, and they will do the real-time trades. And now we need to settle this on the real blockchain. So the enclave is going to create this transaction that goes into Bitcoin, the other transaction that goes into Litecoin. In the first transaction, Alice has the 1,000 Bitcoins, and it's controlled by the public key of the enclave. So the enclave will say in this transaction, this 1,000 Bitcoins go to Bob. The other transaction, the 300,000 Litecoins, in the input controlled by Bob, in the output controlled by Alice. Also, just for the illustration, let's say Carol is trading 1 Bitcoin with Dave. So she has 3 Bitcoins that she deposited. So in the output, she still has 2 Bitcoins, and Dave will have 1 Bitcoin. Dave has 300 Litecoins, and he's giving those to Carol in exchange. So those are the 2 settlement transactions that need either both of them need to occur or not. However, what the trusted hardware gives us that everything that is inside the CPU, the secure enclave, we can assume this is secure. However, an attacker will just listen to the network traffic that goes out of the server computer. He can filter one of these 2 transactions and destroy it and let only the other transaction go through. So I say that this attacker is a friend of Alice, so he will let only the second transaction that goes on the Litecoin network to go through. So the transfer of ownership of these 300,000 Litecoins will go from Bob to Alice, but the transfer of ownership from Alice to Bob will not go through. So in effect, Alice has stolen $4 million from Bob. So we really want to prevent this kind of an attack. And let me try to give some instructive example why this is not trivial to do. So here is a simple idea on how to do it. We will use the fact that information that goes on a blockchain is public. It's a public blockchain. So this transaction, TX1 and TX2, we are going to embed small arbitrary piece of data that is some symmetric random key. And what we are going to do, we are going to rely on some number of servers, and we say if at least one of them, these servers, is OK, then everything will be secure in our protocol. So this enclave is generating this transaction, TX1, TX2, that embed this fresh symmetric key inside of them. And the enclave first sends an encryption of both TX1 and TX2 into these servers. So far, the actual data, the sensitive data, is not known to anybody, only to the enclave, because everything is encrypted. After the enclave receives acknowledgement that all of these servers have the data, then it releases in the clear this transaction, TX1 and TX2, to be submitted to the respective blockchains. And now, if one of the transaction is actually goes, let's say, into Bitcoin, then all of these servers can see the symmetric key that is inside this transaction, and they can decrypt the data that they already acknowledged that they received, and then get the other transaction and put it on the Litecoin blockchain. So if at least one of the servers is honest, this is supposed to work. However, this doesn't work because of a race condition that is a little tricky to explain in a short talk, but basically, an attack, the problem is that it's in this big illustration that we really want it to be the case that if nothing happens, like I deposit money to the exchange, after some time I can get the money back if you just destroy the exchange server. So in this kind of a protocol, what will happen is that an attacker will just see the first time that one of the transactions is sent to Bitcoin, So he knows this secret key, this secret symmetric key, but he's not revealing anything, and he's just sending a transaction in the last moment, and then there will not be an opportunity to send the other transaction to the other blockchain. So this kind of a simple protocol will not work, and we need even more complex protocol. So this is a theoretical solution that is even more difficult to explain, where you need to use the scripts of the cryptocurrency. The scripts is allowing the money to go through only by verifying that an event happened on another cryptocurrency. And this is okay. It is straightforward enough to do in a blockchain that is based on proof of work. In more complex blockchains, it's become even more difficult. There is some probability analysis that this is as secure as the cryptocurrencies themselves. But unfortunately, for Bitcoin, you need an extra feature that Bitcoin doesn't have, so we cannot actually implement the theoretical protocol on Bitcoin. There is a practical protocol that we are implementing that is using multiple number of other servers that also have that are also SGX enabled, that also have trusted hardware, and then we can get really nice feature for this real-time exchange, including the last bullet point. So the one before last is that we can also support, let's say, proof of stake-based cryptocurrency that you need to prove to the enclave more complex conditions. The last bullet point is important. It has a very scalable version where the settlement data that you commit to the blockchain can be even a single hash. So this can be very scalable under quite mild trust assumption. So this is what we are implementing. And also, when you have these servers that ensure this all-or-nothing fairness of this, all the data, either all the users get their original money back or all the trades really happen. So we can also use these servers for what is called a state machine replication against denial of service attacks. So if one server is being attacked and the users cannot communicate with the server, then the other server will see that that happened, and they will switch, let's say, to a new leader, and they can take backup that is very recent, let's say, from the last 5 minutes when the other server was not under attack yet, and continue from there. And then without any human involvement, we can make sure that the exchange service is always running with this replication of the data among several servers that have trusted hardware and back up all the exchange data in their secure enclave. So it's not known in the clear. It's only known inside secure enclaves that are communicated in secure channels among the enclaves. Okay, this is the last slide. So this is a nice idea that some of the PhD students that are working with me came up with. The idea that what we can also do is what we call tokenized assets. So, the way that this is working, instead of, let's say, just trading Bitcoins for Litecoin, so let's say I have Bitcoins, I'm going to trade these Bitcoins into issuance of new tokenized Bitcoins on another blockchain. So let's say I deposit Bitcoins that are residing on the Bitcoin blockchain, and I'm going to get in return a tokenized Bitcoin on the Ethereum blockchain. That those tokenized Bitcoin did not exist before, but the enclave is going to issue those new tokenized Bitcoins without any human involvement. And the Bitcoins that I deposited are kept into a reserve that is being committed to the Bitcoin blockchain, and this reserve is controlled by the secret key of the enclave and not by any human. And we can get this scheme, we get with the secure protocol for this all-or-nothing settlements, that we get this guaranteed solvency that you can always, if now these tokenized Bitcoin are circulating on the Ethereum blockchain, that anybody who gets these tokenized Bitcoins can go back to the exchange service, redeem those tokenized Bitcoins for the real Bitcoins that are that exist in this reserve output, and get the real Bitcoin for his tokenized Bitcoins. So we get this one-to-one reserve guarantee. And so use cases for this is, so what can you do on let's say, an Ethereum blockchain that supports smart contracts? So let's say another project that I have is about how to play a trust-free poker that doesn't have any dealer that you need to trust to give you the cards. So now you can, for example, play this poker on Ethereum, but use tokenize Bitcoin as the chips instead of using Ether as the chips that you win or lose during the game if you want. So this is just one example. Another example, if you want an ICO to raise money, you can raise the money in Ether. Like Ether can be sent to the contract, but now you can also, let's say, if you want, you can send this tokenized Bitcoin to the contract. So it's a little easier to do this contract for an ICO on Ethereum than on Bitcoin. So this allows you to do that. Okay, so that's the last slide. So let me just say, so this is a project that so we have an implementation demo of this project, and we are trying to implement a version of this that will actually be deployed in the real world. So yeah, I'm working on this with several students. Okay, thank you.
Thank you. Thank you, Idon. As you can see, the brightest minds in the world are working on these problems. Back in the 80s, if we go back to front running, which was the topic here, back in the 80s, front running was actually the model that traders used to make money. So traders like me, I was born, but I was very young in the 80s. So at some point in the 90s, front running was actually forbidden by law and would get you into jail. But nowadays, with blockchain, it appears to be legal again, or at least a lot of people do it and try to do it. So that's why I'm very happy that the brightest minds in the world are working on fixing this, because legislation won't get us there. But we need people like Ido and all the other speakers to solve these problems. Next up is Nikos Leonardos. He's from the University of Athens. Also a very bright mind. The stage is yours.
Thanks.
Good luck.
Okay. So I guess I'll have to time myself. Huh?
Yeah, if you want, I can.
A bit dangerous, but okay. All right. So I'm Nikos, and I will be presenting work that is joint work with Juan Garay, who is sitting over there and is speaking next, and Angelos Kayas. So this is work that is going to focus on Bitcoin, but I think it makes sense for any proof-of-work-based blockchain technology. So let me start by first saying what Bitcoin is for me. So Bitcoin, first of all, is an algorithm, a distributed algorithm, and it's an algorithm that has solved two problems. The first one is very well known. It was an open problem. It was the first decentralized cryptocurrency. The second problem Bitcoin solves is an old problem, fundamental and very well-studied problem in distributed computing, the consensus problem. If you open a book in distributed computing, a good portion of it is devoted to consensus or related variants of this problem. So I think these are good reasons for the academic community, for researchers to want to really understand this algorithm and be able to analyze it. And what I'm interested in is giving a formal analysis of Bitcoin. And what this means is providing very precise definitions of an environment in which we want to describe the algorithm, of the resources of the algorithm, the resources of the adversary. We want to define precisely the properties that the algorithm should have. And finally, and most importantly, we want to give a formal argument. We want to give a mathematical proof that a suggested algorithm, the Bitcoin algorithm, has these properties. So a few years back, we did some first steps in this direction. And in some specific setting, a static setting, we managed to do this. There was a lot of follow-up work. The point is that work so far referred to a static setting where there was a given number of participants and no more, no less than that in the whole execution. And this is not how Bitcoin works. You know, people can join and, or leave the Bitcoin network. And we would like to have a proof in this dynamic setting. So there has been some recent progress in this, and if I have time, I might speak about this. But my main goal in this talk is to give you a flavor of what it means to have a formal argument, a proof about a property of the blockchain. So I'll try to do that now. And let's start by discussing what's this environment we're going to analyze the algorithm. So one way to think about this is that all of us here want to run Bitcoin, want to run a Bitcoin network. And you can think of it as we all have in front of us a recipe, a Bitcoin recipe, which tells us what to do. And we're going to work in rounds. So there's a big clock counting the rounds. Big Ben says it's round one. It's round one, so we execute our recipe. And we communicate. A round is gone, and second round, we execute our recipe, the Bitcoin recipe. We communicate. Then round two comes, and so on. And the only assumption is that most of us are honest. But we cannot really trust anyone, and we don't really know things we hear from which person they're coming from. So maybe it's a dishonest person saying something, we have no idea. And you can actually think of the dishonest people as an entity, the adversary, who has the power maybe to whisper something in your ear, and nobody else will listen to it besides you, but you don't know that. So I think it's remarkable that doing this in this environment, Bitcoin manages to solve this problem, and actually, as some person here agrees with a person back there about what transactions have been made. So let's see what it means to prove something about in this environment formally. Okay, so I don't want to go into details. You probably know about the blockchain, but I just want to make it clear that what each one of us has in his brain when we're doing this is a blockchain. That's all. So it's a sequence of blocks. And the only thing we're going to need in our analysis is that it's hard to compute a single block. And for the analysis, we're going to model this. You can think of this as just a coin flip. So you want to compute a block for the blockchain. You can think of it as flipping a coin, and with a very small probability it's successful, and you manage to extend your chain. And with otherwise you don't. It's unsuccessful, and you don't manage to do anything. Another property is that you cannot really tamper with the blockchain. And what's the recipe we're running? The Bitcoin recipe. So we are, when round 5 comes, we're listening to the network for blockchains. That's what we're listening. We take all these blockchains we listen to. Some of them might be coming from the adversary, who knows. And we're keeping the longest one. And then we engage in this coin flip we were talking before. We just flip our coin and see if we are successful. If we are, then we extend our chain and announce it to everybody. So this is the game we play. And well, let's keep this execution example to save some time. And let's talk about what properties now we want this algorithm, this recipe we're running to have. So one property at the application level, at the transaction level, is persistence, which basically says that if a given transaction is ever confirmed by a given participant, then every other participant will see these transactions at the same place at the ledger. So this will allow us to agree on what transactions are confirmed, and we can spend money. Let's just focus on this one. There are other properties you can define, but let's focus on this property. And next, what I want to do is define a corresponding property for the blockchain. So we are going to prove something rigorously. So I want to have a property. We are going to prove things about the blockchain. So I want to have a property for the blockchain. So the corresponding property we call a common prefix. And what common prefix says is that at any given round, any two honest parties will have chains, blockchains that share a large common prefix. So maybe they're different, but they're only different near the end. They not have really, the chains will not differ too much. So this is the property I want to focus on, and I would like in the rest of the talk to give you a feeling of how we prove formally that the blockchain that Bitcoin has indeed has this property. So we're going to prove this lemma. We're going to prove that in an execution of Bitcoin, this bad picture over here almost never will occur. So here we have two chains, two blockchains, and they differ on a lot of blocks near the end, right? So this is something we don't want to have, of course, right? Because something like this might allow to someone to double spend. So if at some point I can convince you that we both have this chain, and I can convince you that over here I gave you some money, and then later on this chain becomes the longest one, this money are gone. Okay, and I have managed to double spend. And in any case, if you have this picture, it's not clear how we can agree on things, because if I'm on this chain and you're on this chain, we're looking at different transactions, so there is no agreement. Okay, so this is a bad picture. Let's see how we can argue formally that does not occur. The main observation is the following. So recall that to produce a block in the blockchain is a difficult task. And we're simulating with a coin flip, which is successful with very small probability. So most of the time that a new block is computed, it will come from a unique participant in the game, a unique player. So we're going to call such a round a uniquely successful round. So it's a round where exactly at most one honest party managed to compute a block. So if computing a block is hard enough, most of successful rounds will be like this. And the observation now is that if a certain block, say on the upper chain, was computed at a uniquely successful round, then the corresponding block at the other chain must have been computed by the adversary. So to put some pictures here, so suppose the blue blocks are blocks that are computed at uniquely successful rounds. So an honest party, a unique honest party at a given round managed to extend the chain. So he was trying to extend this chain and managed to get this block. Then what this observation says is that if you look at the fork, at the same position, this block must have been computed by the adversary. Now the importance of this observation is that you can pair blocks. You can pair honest blocks with adversarial blocks. But then this means that the adversary has computed as many blocks as the honest parties. And our assumption is that the honest parties have collectively more power than the adversary. So how can this happen? Okay, so after some details, what you end up with is a statement that says that in a given set of rounds, the adversary got as many blocks as the honest parties. And this cannot happen. This is like you're playing a game with a friend and you have a coin that is successful with probability 11%, and your friend has a coin that is successful with probability 10%. And you're flipping your coin for 100,000 times. Then you are expected to get 11,000 successes, and your friend is expected to get 10,000 successes. So there's a huge gap of 11,000 successes, which is difficult to cross over. So it's difficult for your friend to win this game. So this gives you the result that this is a very low probability event to happen. This is very unexpected. Okay, so two remarks about this. One is that this works for any adversary. Okay, so we made no assumption about the strategy of the adversary. Nowhere in this argument that said the adversary might be doing this or that. So this is good. This is one thing our proof should have. And the other, even if you didn't follow this argument, another thing to take away is that the argument relied a lot in the fact that computing a block is hard. So proof of work should be the harder this proof of work is, the more secure the protocol is against double spending, against this property. Yes?
I have two questions. One of them is there is an assumption here that every round was uniquely successful, but honest parties they can fork by mistake. So you didn't seem to have modeled that part.
No, exactly. No, this is what you say is true, but what I'm saying is that when the task of computing a block is very hard, then what you're saying is a very low probability event. And if the power of the adversary is bounded away from 50%, then the advantage he gets over such events is not going to be enough to get over this disadvantage the honest parties have. Okay. So as I said, this is an argument that works fine in the static case. In reality, things are different. So more people are coming in. So the power in the system changes, and this means that. So if you were keeping the task of computing a block with the same hardness, and at some point people were investing in hardware, in mine hardware and stuff, and this task of computing a block was getting easier. Then the argument I had before is not good enough, exactly because of the reason that came up in the question, right? Because the easier it gets, then most often you're going to get a situation where the honest guys fork by themselves, and it's going to spoil the argument. On the other hand, if a lot of people leave Bitcoin and block production drops, then it's not usable anymore. So what happens in reality is that Bitcoin tries to get a constant block generation rate, about 1 block per 10 minutes. And it calibrates the difficulty of computing a block in order to achieve that. So we want to analyze Bitcoin in this setting. And in this setting now, each block is associated with a different hardness. And now people follow not the longest chain, but the heaviest chain. I'm going to skip this, but I just want to say that basically the same argument kind of works, and you can arrive at the same inequality, at the same event. The problem is now that if you think about the corresponding game you were playing with your friend, now because you haven't really proved anything, and the adversary can maybe manipulate the target, maybe can manipulate the hardness of computing the block, then it's like in your game your friend is choosing the probability of your coins. So maybe he's still choosing them in a way that you still get an advantage, but he's choosing the probabilities. So say he's choosing he's choosing a coin for you that is successful with probability 1.1 out of 1,000, and he has a coin that is successful with probability 1 out of 1,000. So your relative advantage is still the same. But now if you play the game for 100,000 rounds, you're expected to get 110 solutions, successes, and your friend 100. So the gap now is smaller, and you cannot argue that this is a low probability event. So there's more stuff you need to do, and you really need to study how Bitcoin adjusts the difficulty of producing a block. So what Bitcoin does basically is it looks at every 2016 blocks. It says now you need to see what the next difficulty should be, and it does something very simple. So basically what it says, so these 2016 blocks come out every about 2 weeks. So what Bitcoin says is that if instead of 2 weeks it took you 1 week, then I will make it twice as hard to generate that block. If an epoch came out in 4 weeks, then I'm going to make it 2 times easier. So it's a kind of a linear relation. Now, it's interesting that if Bitcoin was doing just that, then there is an attack. And if there is an attack where an adversary could manipulate the difficulty and actually create a large fork. But it seems that Nakamoto knew this, and this is not exactly what Bitcoin does. It does something more. It still uses the same linear relationship, but it says something more. It says that if, say, if you have a chain and the last epoch was finished in just 1 day instead of 2 weeks, then Bitcoin says that, no, I'm not going to do the task 14 times harder. I'm just going to stop at 4 and make it 4 times harder. Or if it took too long, I'm not going to make it more than 4 times easier. So it has this threshold. And this seems to rule out the previous attack. But then it's unclear. It might create some more problems, because what if if the power really changed by 15 times? What then? What if it's constantly increasing by 15 times? Then this does not seem to catch up. So what kind of thing are we going to prove in this case? And the reasonable question to ask is, can we prove security under one more assumption? Besides the honest guys having the majority of the power, we need one more assumption that says that the number of parties is not changing very widely. And we can get some theorem in this direction. So it is possible to prove that if you look at 2 rounds that are not too far apart, then if then the number of parties is not too far apart, then you still can prove the same properties for Bitcoin. Let's skip a sketch of this argument. Let me get to the final slide and just say that so we have managed to do some progress there, but it's not very satisfactory. It really doesn't say much about real parameters, about real Bitcoin. So it's more kind of a theoretical result, and it would be very nice to have a very clear argument that makes sense gives good parameters. And another important question that I like, very fundamental, is so Bitcoin uses this specific target calculation technique. Is it the best? Can we find something better that might allow us to do, to allow faster block generation rate, or allow us to handle populations changing more widely? I think this is an interesting fundamental question, and I'm done. Thank you for listening, and more questions, I guess.
Thank you, Lucas. We have 2 more talks before the coffee break, and all the speakers will be here all day and very open to talk with everybody here. And I think there's a lot to talk about. The next person is actually also working with Nikos. He is from Texas University, Professor A&M, sorry, Texas University A&M. It's Juan Garay. He's setting up his computer. And I think what is interesting to mention about Juan's history, he used to be a principal research scientist at Yahoo, but also worked at AT&T, Bell, and IBM, I believe. So you have a long history in your career already. And he is a very well-known cryptographer, also author on several books, I believe. Right? Are you set up? Almost. Okay. Then, in the meantime, maybe we can do a small quiz. So I'd love to learn more about you as well. It's kind of like, whom of you own some sort of cryptocurrency? Raise your hands. Okay, so there are actually quite a lot of people also that don't own anything. So now it becomes interesting. Whom of you, there's a saying, kind of like everybody is into crypto right now, but no one of your friends owns more than 3 Bitcoin. So whom of you owns more than 3 Bitcoin? Okay. Yeah. So nobody of these are my friends, because that's the saying, right? And another thing is kind of like who stepped in December. Some of them, because it's always nice when you step in and you know, basically any trade you would do would be a great trade because, you know, the price went up. But as of December, of course, things have been changing a little bit, and it's not that easy anymore to well, still you can still make money on it. Are there? Let's see. Who can I hear like altcoins that some people are into that are not like in the top 10 or top 20? So just which one? VeChain. Yeah. Did it do well for you? I see you with a big smile. So okay, VeChain. Other ones. Waves. EOS, yeah. Never heard of that one, but I'll look it up. Real blocks, yeah. Ray blocks, yeah. Medici. Is that from the family Medici? Medichain. Yeah, Medichain. I'm also an avid gaming fan. I'm just talking because we're not ready yet. I'm also a gaming fan. I recently bought some Unicoin, which is, I think, not in the top 200 cryptocurrencies at the moment. But it's an interesting coin as well. I think Juan is ready. Later on, we'll try to figure out how much coins we own combined and to see if we can actually buy this whole building. Good luck.
Thanks. Hello, everybody. I'd like to thank the organizers for inviting me here to the great city of London. That's me. You got it on the... All right. So the title is a little bit catchy in the sense we wanted to call this "But Why Does It Work?" And the rest is more technical stuff that I get into. It's a sort of rational crypto analysis of Bitcoin. This is joint work with Christian Badertscher from ETH Zurich, Uli Maurer, also ETH, Daniel Sudi from Aarhus University, and Vasily Sikas from Edinburgh. And this is a paper. The full version of the paper is going to appear in a conference called Eurocrypt, which together with crypto is one of the top 2 conferences in cryptography. All right, so a little bit of motivation. I have a lot of material here, which I'm going to gloss over and skip, but you can look at the slides later, as Patrick said. So the motivation, digital money transfer, or more, as we'll see, and the accounting is implementing a ledger, which is what Bitcoin does. Here's a pictorial representation. We have a Genesis block, and this doesn't work on the... Okay, Genesis blocks, right? And then we have simple transactions, or we can have complex transactions on the blocks. The contents can be provided by any user with sufficient funds. As we already saw, anybody can see, what's going on in this public ledger. And there is, bad behaving guys, the adversary, who, might try to do something mean. Okay, but this data structure should be, prevents from the adversary from making malicious modifications. And we get more into these details later. Okay, there is an update. This thing evolves, grows over time. And there's been a lot of attempts to address the security of Bitcoin. Okay, so we started early on. And there are fewer, perhaps, analyses that, try to make a, more rigorous, and, give us a more rigorous understanding of what's going on. For example, this is the stuff that Nikos just talked about, and some other examples. But the main conclusion of these works is this thing, Bitcoin works if and only if the mining, a majority of the mining power is honest. No?
Selfish mining showed that that's not true.
No, that's right. We mentioned initial, semi-analysis. Professor Sear also showed that selfish mining shows that what Nakamoto promised, right, was not true. Okay, and that we reflect in this rigorous analysis as a property called chain quality. And that means that if there is a certain proportion of miners trying to insert transactions, that's not going to work. According to what Nakamoto promised, it's going to be much lower than that. Okay, so this is taken into account into this thing. So there is properties, as Nikos mentioned, common prefix, chain quality, and all these properties that this data structure should satisfy. Okay, and some of these properties, parameterized, work if there is an honest majority of hashing power. Okay? And let me just gloss over this. What does rigorous analysis means? You have to define a model, rounds, computational model. What does it mean for a proof of work to work? There is something called a random oracle. That is how proofs of work are done in Bitcoin. Defining these proofs of work is it's a task. Okay, you want to be more formal about it. What does it mean? There are witnesses, and this should be not so easy, like not too hard. This is also called moderately hard functions. Okay, and the verification of this proofs of work should be easy. So this means the rigorous analysis means defining all this stuff. And as Nikos mentioned, now you come up with these properties that the data structure, the blockchain implemented this public ledger should have. And properties are common prefix, chain quality we just mentioned, meaning how much are guys who are following the protocol, maybe what proportion of transactions should be from these honest parties. Okay, and then there should be a chain growth, meaning that parties are trying, so this data structure should grow. Okay, the example of common prefix, this cauliflower type of picture, things might diverge because the system is distributed. Different miners might have different views of the data structure. Okay, but if there should be a prefix, and everybody should have the common view of that prefix. And chain growth is another picture. The thing should grow. Okay, and example of what Nico was mentioning, then you're able to prove that no matter what the adversary does, okay, controlling some of the parties, some of the miners, then this common prefix is going to, if you let the chain grow, the blockchain grow for k blocks, then you're going to have this with big probability, or the error will be exponentially negligible probability in the number of blocks. Okay, and this is provided that there is a majority of honest hashing power. Okay, this is what alpha means, honest majority. Beta is the bad, hashing power. The binaries are controlled by the adversary. And this lambda thing, we would like it to go to 1, meaning that when there's a majority of honest majority of hashing power, then everything should work, and then we can prove these theorems. Okay, so alpha, beta, we come back to this relation between good and bad power. And doing this, doing these properties, proving stuff about these basic properties, common prefix and others, then we can come up with properties of the application, the Bitcoin being one of them. So implementing a public ledger would follow if these properties are satisfied. Okay, so that's good. Motivation, this is what the more rigorous analysis being showing. Okay, so things work if there is an honest majority, except that we have a situation like this. Okay, this is a picture of mining pools, many of them in, say, China. Okay, but what would prevent these mining pools from colluding, and they can easily achieve a majority of computational power? Right? Again, we prove things assuming a honest majority, but look at the real situation. So this is the honest majority thing was what the cryptographic analysis gave us. There's been other attempts to model this thing, Bitcoin and blockchain from a purely rational point of view, assuming that every agent, every miner is by itself has its own incentives. Okay, there is a lot of work also in this department. And usually their conclusions are as or more negative than this honest majority thing for the solution to have an equilibrium. I mean, in game theory, you talk about equilibrium, how the system is going to keep working and parties are going to continue to work. Okay, so that's the situation. The theoretical results, the rigorous analysis tells us one thing, yet the system keeps working. Okay, there's been no major fork or substantial slowdown attributed to this cryptographic or rational attacks. Okay, and it seems to be performing according to specifications, to what Nakamoto envisioned. So here's the questions that we ask. How come? How come is this happening? And the other question is, the first question is, how come miners who might deviate from the protocol are not doing it? And then the second question is for the honest parties. Why do honest parties keep mining? Okay, so those are the basic two questions that we address in this talk, and that's why the title of the talk is, but why is it working? So this is what we do. Again, we have a rigorous attempt to do a rigorous analysis, cryptographic analysis for these questions, and using something that we call a rational cryptography approach. Okay, to capture these economic forces, underlying this process. And for this, we assume that the parties would have natural incentives. Okay, one is financial, incentives. We want to, make money out of this, and we have a cost that says, we have to pay for doing this. Right? We have electricity costs. We have to buy mining hardware and so forth. Okay, so those are incentives and the cost. And as a result, restricting ourselves to these incentives, we show that we can do away with the honest majority assumption. Okay, I'll show you more details later on. An enabling tool for this is something that we designed a few years ago called the Rational Protocol Design Framework, okay, together with some of my co-authors. Okay, so we apply this framework to capture these incentive-driven attacks. The incentives are, we want to make money, we want to get block rewards and get utility from the fees that the miners charge for transactions to be installed. And the penalties, as I said, would be, we have to pay for this. Okay, there should be a, a trade-off, a balance between what we spend and what we make out of mining and perceiving block rewards and transaction fees. Okay, and similar incentives we have to do for the designer. Okay, whoever designed this protocol and makes honest miners parties to continue to grow, to do the work. Okay, so we have to model these incentives for honest parties to keep working. And that means that this we end up in something called non-zero sum game, okay, because they not cancel each other. Okay, so the incentive of the honest miners doesn't mean that it's just to prevent the adversary to blow out the system or not make it work. All right, so that's a non-zero sum game. And for this, we need to extend this framework to new security and stability notions. Is anybody going to tell me the time, or is that the clock? Okay, so I hope this is clear. We have this honest majority result that says if there is an honest majority, things work. And now we're saying, well, there might not be an honest majority. What prevent the mining pools from colluding and acting, by themselves and not following the protocol? Okay, and this is what we show applying these incentives and modeling these incentives and penalties. And so we analyze two cases. As a warm-up, we just say what happens if we just consider the case of block rewards. Okay, there is a reward just for solving proofs of work and installing a new block. Forget for now about the transaction fees. And we show that in this case, the system is secure, performs according to specification, and that is incentive compatible. The case of block rewards plus transaction fees is a bit different. And here we have to take into account, some considerations. For example, if the abundance of transactions is big enough and there are no limitations, then we get essentially the same results. Okay. Now, if we know that bitcoins are going to be exhausted and then block rewards might disappear, so you just have to focus on transaction fees. So there, the situation is a little bit more different. It might be the case that if there are not enough transactions, okay, then you cannot guarantee security as that would allow the system to keep working. In which case, we can have to fall back to the honest majority assumption. But if that doesn't happen, we can do away with the honest majority assumption. Okay, so in the 5 remaining minutes, are we taking into account the time to set up the laptop and stuff, or?
There's still 5 minutes.
All right. Don't waste it. So the main takeaway of this would be, let me show you a little bit what this framework, RPD framework, means, because I think it's useful for cryptography in general to prove realistic results in crypto, as well to cryptocurrencies and blockchain. So for that, I have to tell you how you would prove a cryptographic protocol, secure these days, and that's comparing two worlds: the real world and the ideal world. The real world is where the protocol is run, and the ideal world is an idealized situation where there is a trusted party doing the computation. Okay, and there is a distinguisher, Zeus in this case, that's trying to distinguish the two worlds. And the thing is, this world is ideally secure, okay, because this is a trusted party, parties send inputs, and then they get the outputs. Everything's ideally secure, and this is a mess. But if Zeus cannot distinguish the two worlds, okay, then the protocol should be secure. That's intuition, and here's an real-world adversary corrupting parties in the real world. Ideal world adversary corrupts the same parties, and he tries to make that these two worlds are indistinguishable. Okay, the traditional thing is, doesn't matter what the real-world adversary does, Then there exists an ideal world adversary called the simulator that is going to make this indistinguishability thing happen. Okay? So notice that this is for all adversaries. Okay? Totally, unleashed. He can do whatever he wants. All right? That's the crazy guy picture there. And we know if we do this, we have strong impossibility results to do things, in particular in secure multi-party computation. In fact, we also need a knowledge majority for that, which is reminiscent of what we need for Bitcoin and blockchain. Okay? But if we do this more refined focused adversary analysis, we can do better. And this is what we did in this RPD framework design back in 2013. So incorporating incentives to the adversary. So this is the crazy adversary. Is doing anything he wants. Instructing the parties he controls to do everything he wants. And this is the rational adversary, the purely rational adversary that models parties as independent entities with their own interests. Okay, and they all have their own interests to follow. Okay. And there's been a lot of work in this rational protocol design as well. And in fact, what we want to capture this security with incentives, what the rational approach has been doing is this. Okay, and what we are doing, and it has some complications, what we are doing is this. Start from crypto and get security with incentives. And this is our approach. All right, so instead of the adversary trying to break anything he wants, he has some incentives. Okay? In more detail, we can model this as a two-party game. This is called Stackelberg game in game theory, where the protocol designer, say Nakamoto, makes a first move, and the adversary makes the next move. Right? It's a two-move game. And then we can show some sort of equilibrium when things are secured, when things are going to work according to the utilities that we define. Okay? Notice that in this, the way we formulated the framework is a zero-sum game, because the protocol designer is trying to totally block the adversary. Okay, here we have two types of things. We want the adversary not to be able to corrupt things, and we want the honest parties, the protocol designer, to make the honest miners to keep moving, to keep working. Okay, so we have to adjust the definition of utilities and everything so that to capture a non-zero-sum game. All right, so again, RPD captures these utility-relevant attacks to the protocol, and we have a methodology of doing that, which essentially, I mentioned this ideal world situation. We define, this is technical, we define attacks in the ideal world, then we define payoffs, and then we map them to the real world. Okay? So in the interest of time, this is what we do here, but let me just go ahead and you can have all the slides, okay, the deck of slides to look at. So let me move ahead. And I'm going to show you first utilities. There is a little bit of math there, and what all the terms come from, and then what the connection between the cost and penalties are. Okay, remember, we are trying to do this RPD analysis for ledgers, so we go through these steps. First, we have to come up with a defile functionality for a ledger, okay, which models the attacks that the adversary can play in the ideal world, okay, to this functionality. One is, remember, we have this blockchain is a linked list, So this functionality should allow for trees as forks happen. Okay, so it doesn't restrict the adversary much, and makes whatever possible efficiencies you might think of possible. Then here's the math coming. So we have to define the utility of the attacker. There's a bit of math here, but I tell you what all the terms are intuitively, and then the utility of the designer. Okay, so let's see if I have this. Never mind that. For example, see that this stuff is being added up, because this is the rewards that parties, both the honest parties and the adversary, get for inserting blocks in the chain. Okay, and this is all probabilistic stuff, right? This proof of work, as Nikos was saying, is a random, coin toss and stuff. So this happens with some probability. You have to model up with random variables and so forth. But this stuff is added. This is the cost that the modeling of the cost that the parties have for producing proofs of work. Okay, so remember we have this queries to the to the hash function to try to solve a proof of work. So this has a cost, and that's why it's subtracted. And this is the penalty that the honest party would pay if it allows for a fork in the chain to happen. Okay? So a lot of math, but intuitively this is what happens. You add for good, good events provide utility. If you have bad events, that's a cost. And we have the same situation for, this was the case for without transaction fees. If you have transaction fees, you have the same type of situation, where now you are getting a reward for installing transactions and collecting fees. Okay, and this 10 to the minus 8 is a Satoshi unit, so the transaction fees are multiples of this unit. Okay, so you get rewards for generating a block and for installing transactions, and you have to pay for mining. M cost stands for cost of mining, and the same thing for the designer. Okay, for the good guys. So here's one of the conclusions. Under these assumptions, Bitcoin is what we call secure. In that sense, the adversary is not going to deviate from doing what it's supposed to do. Okay, never mind the attack payoff strong and so forth. So essentially, it doesn't do anything. It can collude, have a mining pool, but all the parties keep mining. Okay. In fact, going back to the selfish mining question, we can think of, we can explain why chain quality is much better than it should be according to selfish mining. Same thing for the designer. So why are the honest parties continuing to work? So we show that in this case, that's what they do, and we achieve stability. So meaning that the honest parties continue to do their work. Okay, and we can show some sort of equilibrium between these two things. All right, so so we have stuff that gets added, stuff that gets subtracted. Then you do a calculation, and you can conclude that it's always secure. And it's going to be incentive compatible, provided the rewards that they get is bigger than this amount, okay, which is the cost for solving proofs of work over the probability of getting lucky, okay, being able to solve a proof of work. Okay, this might be a small thing. Okay, so as long as the reward, and this stands for conversion rate, meaning because this reward is in blockchain, is in Bitcoin, you have to convert it to US dollars, euros, or something. So as long as this stuff is high enough, you're going to get these two situations, these two conditions. With transactions fees, as I said, it's more complicated. If you have no restrictions, then things Bitcoin is secure. And incentive compatible if you have these other conditions that there's going to be an upper bound on the maximum transaction fees that can be charged, and importantly, availability of transactions. Okay, as long as there are enough transactions coming in, with this transaction fee structure, then the system is going to continue to work. Okay, but as I mentioned, if there are not enough transactions, then this would not be true, in which case you have to fall back, you have to rely back on the honest majority assumption. Okay, and I have the references coming up for details, but that's the main conclusion. So we try to answer these questions. Why does it work? Okay, given that how could you guarantee an honest majority of computing power, given the picture I show you about mining pools and their size? We extended this rational cryptography framework to do the analysis. We looked at these natural incentives, making money and paying for your costs. And this works even though, as I said, a majority of collisions are possible. And we think that these incentives are natural. And we extended this rational protocol design framework to capture, these blockchain-type protocols. References, this, as I said, is going to appear in Eurocrypt. And there is a bunch of background references on which we build on. All right, so thanks.
Thank you. So we have one more presentation before we go to coffee. What I always love is if, like Juan said, and now it's going to be a bit technical. And I was like, huh? But that was the whole talk. Anyway, so very, very interesting. Our next speaker, and this is the last talk before we get to the caffeine part of the day, is from IBM, Ross Cruikshank. Come up on stage, Ross. I have one question maybe. Anybody here from an academic background? Yeah, quite a lot. Developers? Yeah, also. Business? Also, okay, so most of the business people will have a hard time understanding everything. I try to figure out that mathematical formula, but my mathematical formulas contain plus and minus and multiple. But that's about it. Ross, you're more on the developers and the business side of things.
That's right, Patrick. Thank you.
Take it away.
Thank you. I will be quick, I think. I've got 40-odd slides in traditional IBM style. I'm going to show you probably now about 3, maybe 4. As Patrick said, I'm a developer advocate in IBM, so what I'm looking at is commercial application of blockchain technology rather than cryptocurrency. So what I thought I'd do is get a quick talk about the kind of use cases that we're seeing for the application of blockchain technologies, where it can be used, and to appeal to developers out there who want to actually be able to do blockchain development, help to build up a commercial platform for a particular niche industry, for third sector applications, anything that you think might be worth using the underlying technologies of blockchain rather than getting into the crypto side. Right? The one thing I will say here, anything that that we're doing with our work in blockchain is specifically to avoid things like proof of work. So the idea is the only reason that you should be looking at increased costs for operation is because your transaction volumes are going up, not because you're having to do more and more work to prove that you've done work. Right? So we're trying to get green blockchain and good ethical stuff that's useful and useful at an early stage. Right? So I'll skip through some use cases just to give you an idea of where we are and which industries we're working in. The tools and platform that we're aligned with, and a little demo that you can do yourselves to show you how quick and easy it is to get going with blockchain technologies, but without having to worry about too much about the proof of work, the adversarial attacks, particularly when you're on a permission network. So the whole model here for permission networks is about you choose who you're going to interact with. You know who they are. So the difference being you're not anonymous or pseudonymous. You're identifiable. You're a trusted party, so you're invited to join a network. If through various protocols that are in place for consensus, it turns out that you turn out to be an adversary on that network, or you're trying to defraud the network in some way, then you can be ejected. And the whole idea of these networks is that you're probably part of a supply chain, you're part of some much larger set of organizations working together. If you get ejected, you're kind of ejected from the industry. So there's much more of an incentive really for you to stay on, particularly since you can be identified. So if we don't get to the end and you decide you want to go off for coffee, that's my contact details. If you want to follow up on anything I say around getting access to developer platforms, working with the technologies, trying things out at no cost, give me a shout on either reach me on Twitter or you can reach me on my IBM mail address. Okay. So key thing here is we're looking at blockchain for business, not cryptocurrency. We're not looking at anonymous cryptocurrency. Blockchain for business. Permission networks, people are invited to join. You choose them. They have to kind of be attested. They're probably already part of a partner network or in some way. And if you want to be able to build an industry that says any new entrants to that industry would join that network through a trust mechanism. We were using the Linux Foundation Hyperledger as our core technology. I'll skip over that because there's another one here that says, why is IBM at this conference? IBM has been involved in distributed transaction processing since there was distributed transaction processing. We've been working with blockchain technologies for the last 3 to 4 years. It came out as a kind of prototype offering with IBM's open blockchain offerings about 3 years ago. And IBM basically looked at the market and thought, we could do what we've done in the past, come up with a closed private technology which we control, and then try and get the rest of the market to buy in. Or we can donate it into the open community through the Linux Foundation and get it adopted and modified and improved through open source. So we basically binned the products we were working on and said, nope, we're going to back off and do this from an open source perspective. So since the end of 2016, we've now been working exclusively with Hyperledger as the technology, and we've been using Fabric as the Fabric model rather than the Sawtooth model that Intel are proposing. So there's a couple of mechanisms being used for the trust mechanisms. So anything you hear from IBM, when you hear about IBM blockchain, it's Hyperledger. Right? And we, as of the beginning of this year and maybe the summer of last year, we've been offering a Hyperledger version 1.0 through our cloud platform. You can, of course, since it's open source, you can also download Hyperledger and work with it on your laptop if you want. You don't need lots of horsepower to run this stuff. We have a developer version which you can run in the cloud in a single Kubernetes worker that will let you build an entire network. So I'll show you a demo that you can try from your devices, which is running on a single Kubernetes thread. Okay. So the whole stack here assumes that the blockchain application has been written in some kind of a smart contract language. So it could be native, it could be Golang, it could be Java. They're working on a JavaScript level, or it could be have been generated by the next level up, which is Fabric Composer, which is one of the tools that we're actively working with to encourage kind of high-level application development, like the fourth generation language version of smart contract development and network definitions. Okay, so big membership of Hyperledger. You'll see IBM is in the Premier bit. There's also a lot of technology providers in here, but a lot of kind of financial partners through American Express, and lots of banking, trading partners in here. Right. So all of these slides you can get from it. What I thought I'd do is cover just a few of the sample areas where we're working that are kind of independent of cryptocurrency. So these are about assets, defining assets, being able to track them, and being able to know which parties are moving those assets around, who currently owns them, what states they've changed into or moved from, and having contracts that define what those state changes are, visible to everybody, and those contracts being part of the blockchain. Right. So not necessarily having all of the information about the assets, but certainly tracking the state changes and the value changes through the blockchain. These all assume that these blockchains are for a particular set of industry players. It does not preclude external blockchains, other partner networks, cryptocurrency networks, which all provide information that can be added in and taken out of the chains themselves. Right? So cover those in detail, but the main use cases for us about trying to decide whether a blockchain application is good or not is there a real business problem to solve? Right. What's the fundamental thing that you could solve by using blockchain? Are there identifiable players that would want to be in it? Is there a definable benefit for having those players use blockchain to disintermediate, for example? And is there a compliance regime that would actually benefit from being able to do this? So cryptocurrency assumes that you don't need a compliance regime. These networks assume that there is somebody who should be at some point be able to see all of the kinds of transactions that are going on, all the parties that are involved. So you can know that trades are happening consistent with the legislation. So the contracts may define what actual transactions can occur, but there may be a legislation that says whether those transactions are valid or not. So they would need some kind of compliance regulatory regime, or there's a major player, a market maker, who decides what's right for that market. They just have a commercial weight, but they're the ones who will define what's a good transaction or not. All the other aspects of blockchain that you need, consensus. So the consensus here is generally going to be based on a majority, but you can also use your own consensus. You can have pluggable consensus mechanisms, BFT, PBFT. At the moment, I think that the out-of-the-box model is just simple majority votes across a peer network. Obviously, immutability, finality, and provenance, all of those things that you would like to be able to do, but not have it be expensive, having to go back through the history of a blockchain to find out all of the kind of attempts at anonymization. Actually, the whole idea of these models is that you don't have anonymity, you only have privacy. Right? So there will be keyed access to the transactions for the two parties that are involved and possibly a compliance model, but nobody else should be able to see what was going on. But you may want to expose the fact that the transactions have happened. So all the things that we've been hearing about this morning, about things that you want to hide in a permission network, you actually want to expose in different ways to different people. Not necessarily the values of transactions, but that the transactions have happened. Not necessarily what the asset was, but that some transfer did actually occur. What makes a good use case? It would be something that's limited in scope, but something that if you did it is going to have a net benefit to you. You're not going to have to invest in large amounts of kit to do this. You're not going to have to invest in mining technologies or anything like that. It's simple. IT, ideally hosted IT. I can recommend some providers. But you start with a small business network, so you know who the players are. You know what they want to get from it. They are, to all intents and purposes, honest players. So they are already known to one another anyway, and you have a kind of friendly network. And then as that network grows, then you can bring in more scenarios, extend partners, and extend the network into new areas. That means that it's essentially built on paying for itself to get going from a commercial perspective. Right? And that business that you generate is not driven by fluctuations in currency, it's driven by actual value from the assets that you're moving. Okay? So, digital trading, I'll just do a couple of these. There's about a dozen of these. I'm just going to do one or two. WeTrade is a digital trade platform. So this is things like lines of credit. So this isn't about money. It's about, sorry, it's not about currency. It's about allowing people to spend money they don't have, to move stock around, to be able to do shipping, to be able to get bills of lading based on a line of credit, so that you could build up a history of line of credit, and that then gives you low risk profiles and move on. Right? So there's parties playing in there. None of it has really to do with currency. Global payments, even SWIFT are joining this network now. So the ability to move payments around and having them all cleared. The SWIFT network is joining BBVA, Bank of Canada, all of those parties who are looking at how can you get past settlement quickly. And this is interbank settlement, so it's not necessarily individual transactions. It's those block settlements where you get to end of day and you're moving $150 million from one player to another, billions of dollars over a week, that kind of thing. One that keeps coming up is this idea of financial audit. So you've got your own internal systems and you're auditing, you're keeping your own ledger, but you're part of a network. How can you store that ledger and share it so that all the players who were part of that transaction can see that you are not keeping different records from them about your historical transactions? I'll skip past a few. Know your customer. So the asset here is the customer information. And you might have many players here who are actually the customers. Current state of affairs with GDPR means at some point customers are going to have to be part of a network where the information, actually that point would be May this year, have some mechanism for updating their own information. The last thing you want to do as an organization or as a network of organizations is have different views of what it is the customer is trying to tell you about themselves and what they want to have known. So a shared know your customer repository where the customer can update the state. Anybody who's accessing that information is known. So there's some early work going on with this, mostly Europe. But it's going to come. We've got lots of audit information coming out through in IBM itself about how we're going to handle GDPR. But one of the key ones here is around getting a single view of the customer with ourselves and our partner networks. Have you heard of Everledger and the Diamond network? Okay. High value assets, which you need to be able to prove are the things themselves, because the fakes have just as much shine to them as original diamonds. So what do you do to prove that the asset that you've spent a lot of time digging out of the ground, actually mining, is the one that gets to the customer, and that you're paying the premium cost of the actual mining rather than running an industrial diamond process or slave labor, right? So which is really what this is about, is the avoidance of blood diamond markets, black markets. Okay. So I'll refer to this one, but there's some other things going on around here in renewable energy. There's carbon trading. So anything that you can do to track that you've got renewable energy and sustainable energy sources, that gives you an asset that you can actually accumulate, aggregate, and then you can trade on carbon trading markets, because you've now got proof that you're using sustainable energy sources rather than carbon-based. So you can trade those. And you may be able to offset that by feeding into different markets. So there's a lot of interest in how do you capture this sustainable energy model and use it to commercial advantage. All right. This is the next stage down from what was food traceability. Is all of the players in food traceability now can be members of a network. For logistics partners, think about the unfortunate Kentucky Fried Chicken this week, where the traceability of that food stock, people are going to want to know which of the trucks that have the spoiled chicken in them and which ones are being delivered to where, so that you know that you've got the right kind of food going to the right places, all the way back to the farm, all the way through to the customer. So we're doing that with a number of different partners. Trusted Identity, Food and Drug Administration, Center for Disease Control. So this takes you out more into distributed networks. And I'm not going to talk about this one. I'm going to talk about something else that's not on the slides because it's a group called AidTech. They have their own blockchain technology called OpenChain, which assumes that you're normally disconnected. All of these networks I've talked about with Hyperledger are all synchronous networks. They assume that you can transact and do voting real time to generate blocks onto the chain. OpenChain assumes that you can't do that because you're offline. So you have to be able to do kind of convergent networks eventually. But at some point, they will feed into a centralized real-time network where they can then look for things like AidTech is tracking the disbursement of global gifting programs from major suppliers like Unilever or Procter & Gamble who donate famine relief and humanitarian relief packages. But they want to know that they actually go to the places that they're sending them. And using this mix of OpenChain and Hyperledger, we'll be able to track that right down to disbursement in the field and know that the original donor, knows that their offering has got to the right place and is actually serving a purpose. Right. Hyperledger Composer, the developer tool, lets you define your networks. So this is, rather than writing raw code, you're defining who the players are, who the entities in a network, what the assets are that will be tracked, what the transaction types will be, so basically what the contracts are, what the visibility is, who the players will be, and then generate from that high-level model all the underlying code and transactions, and then be able to distribute that into the blockchain. And do that across a number of different channels. So the blockchain can have a number of different player sets within the chain. So they're using all the same technology, the same shared resources, but they can actually be running as almost overlaid networks, some of which will cross over into each other. All right, so if you want to have a look at that stuff, it's all available. I'm going to skip through these because you can get all this online. If you want to have a look at the demo, I did say there'd be a demo. If you go to the this short URL, ibm.biz BC Coffee, and put in the Genesis device as the network, you'll get yourself on as a trading partner in a blockchain, a Hyperledger blockchain network it's got a simulator running that's trading coffee around the world. You choose what your product is, when you're harvesting it, and how it's going to be traded. And then there's a trading model going on. So you can see the blockchain generating and also what your role in it is. If you want to come talk to me, I'll be around in the IBM booth, little seats outside while you have coffees. Okay? And then the rest, as you'll see, is stuff that we don't need to get involved in. Developer plan is the one I want to show you, which is free stuff. If you're a developer, that's the interesting bit, is it's free. Get it down from GitHub, run it on your laptop, or push it into a Kubernetes cluster on IBM Cloud, or any other cloud that supports Kubernetes. And then the last one will be all the stuff about cryptography. The IBM business blockchain platform is actually built on our Linux mainframe technology, which means you get all the peer networks, all the members can get their peer nodes, ordering nodes, all running on the same platform, all isolated from each other, but all running with effectively minimum network latencies. So you can do synchronous transaction processing in a blockchain network without having to pay for all of the overhead of running your own networks. So if that's interesting, come and talk to me. Thank you very much.
Thank you. So now it's time to get some coffee. We were running a bit late, so we're getting back at 1:15. That's in 20 minutes, but that's enough time to get at least 3 espressos. So you should be good.